Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I am Dr. Sababau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh Universiti Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are still in Chapter 5, Linear Algebra, Matrices and Dirac Notation. In this segment, Unit 5.10, we will discuss Dirac Notation. The objective of this lesson is basically for the student to identify the usage and the properties of the Dirac notation in representing the inner products. Recall that we had defined inner products. What is inner products? Basically, a function which takes a wave function psi and a wave function phi as inputs and produces a real or complex number. It is in quantum mechanics as the output. So basically, if we take two wave functions, then we put them in the inner products notation, then what we get is a real or complex number. Basically a number, because in a number, it can be complex or real. I mean, complex number consisting of the real part and an imaginary part. So basically, inner products is represented by a bracket, and there is a a vertical line separating the two wave function. What we get is basically a C, where C is a complex number. Anyway, in mathematics, many authors use different notation. Other notation being used is just psi, phi inside a bracket, or psi, phi inside what we call this as an angular bracket, or psi with a vertical bar there, phi, then inside the angular bracket. The latter notation is called the Dirac notation. Usually we will use this to indicate inner products in quantum mechanics. Okay. Recall that we had used the Dirac notation for the elements of the vector space, and the inner product was simply an integral like this. I think we had used this before. So basically, this segment is to recall and to revise what we had used. For an inner product between two functions f and g. So basically, it is an integration here, integrals of conjugate of f multiplied by g dx. So this is the general formula, the definition, should I say, of an inner product. Okay. The left hand side, or the bra side, when you write it in integral, it becomes a conjugate. Okay, the function is conjugated, while the cat one on the right hand side is just no change for it. Another perfectly acceptable example of a vector space is the set of matrices, and the inner product is as shown there. We had also discussed matrices previously. So if we have two vectors, okay, so whatever is in the bra are conjugated. The elements of the vectors all are conjugated, while the cat side is not conjugated. And the definition for the bra is usually, for example, like in this case, we have n 1 by n metric. Okay, that means one row and n column, while here is n by 1 metric. Okay. In quantum mechanics, most physicists use Dirac notation. Yes, the angular bracket is being used. In Dirac notation, a general vector is written as, so when you see this symbol, with a bar before and angular bracket after a vector or wave function. So this is basically a general vector notation. This vector satisfies all the properties of a vector space. The sum of two vectors, these are some of the properties of the vector. The sum of two vectors is a vector. For example, if you have vector psi1 plus psi2, vector psi2 should give you another vector psi3. So the symbol here, the symbol for the cat is maintained. Okay. The second property is the product of vector and a complex number is a vector. For example, we have a vector phi1 multiplied by a complex number c, then it should be equal to another vector. That means the product of a complex number and a vector is a vector. Another vector phi 2. So the inner products, now we are talking about the inner products of two vectors, psi and phi, is simply this one, okay? Phi, psi, inside this Dirac notation. Basis set. We had also touched on basis set previously. Suppose that we had the vectors psi1, psi2 until psi n represent an orthonormal basis set for our vector space. So the inner products of of psi from between two psi I, psi j equal to delta ij. Okay, where delta ij is the Kronecker or Dirac delta function. So there is a special name for it. That means if psi I and psi j are the basis set for the vector space, so any inner products of the psi, that means the element of the vector space, will be what you call it, will be controlled or will be maintained by this relationship. The inner products of I and j should be equal to delta ij, and the properties of delta ij is that delta ij equal to 0 if I is not equal to j. That means if the psi I here and psi j are basically two different vectors, okay, in the vector space. While delta ij or the Kronecker delta function or the Dirac is equal to 1 if I equal to j. That means you are doing inner products manipulation of the same, because I equal to j, of the same vectors. For example, like psi 1 inner product with psi 1 2. So it should be equal to 1. Okay, this is just to for us to remember. Orthonormal is basically unit vectors. What you mean by unit vectors? That means magnitude equal to 1 and they are orthogonal to each other. The simplest example in 3D, for example, we have the unit vectors such as ijk, okay, and they are perpendicular to each other. Basically, the direction of the unit vectors are at perpendicular at 90 degrees to each other. This is what we call as orthogonal. So anything which are perpendicular to each other, so basically they are called orthogonal. If the vectors have a magnitude of 1, then it is orthonormal. Okay, so this is the properties for the basis set, basically the elements of the vectors. If they are the same element, you are in a product, you are doing in a product operation of the same of the same elements of the basis set. So it's equal to 1. If it's different, then it's equal to 0. Recall that an arbitrary 3D vector could be expressed as a sum of orthonormal basis set vectors. That means is what we had discussed in previous segments. Okay, so vector R is equal to, actually there is a dot vectors product. Okay, dot products of vectors. We have vector R dot product unit vector X. Remember that unit vector. That what is unit vector? Basically, it just show direction. The magnitude is 1. Okay, and this is also the dot product and dot product. So what we have, dot product will give you a scalar product. Okay, that means just a number, and a vector plus another number. Okay, so basically we can define a vector R is being represented by a constant or number multiplied by unit vector X plus another number or constant multiplying unit vector Y plus another constant or number multiplying with unit vector Z. So the generalization to arbitrary vectors in Dirac notation. In terms of Dirac notation, this what do you call it? A vector phi here. Remember that the del, not the del, sorry, the cat of phi is actually vector phi, and there is a vector psi 1, and we multiply with an inner product psi 1 multiplied by phi. So you can see here the inner product is actually complex numbers or constant, or a number, should I say, a constant. So basically it is similar between the two. You have a number or constant multiplying the unit vectors. Okay, so if psi 1, psi 2, psi n representing unit vectors for vector phi here, so the inner products at each segment or at each section basically just complex numbers. So again, the definition is similar to the previous one. Okay, the previous one basically we limit it to 3D, but for Dirac notation it is unlimited. You can be at any numbers. I mean, you have any numbers of basis set. Okay, so up to n, or n can be any numbers. Okay, so it is basically not limited to 3-dimensional vectors. The constant multiplying the basis vectors are the inner products. So the inner products of psi 1 with phi and psi 2 and until psi n multiplied by phi, or the inner product with phi. So you have written the constant to the right of the basis vectors. This is completely equivalent. It does not matter if we put the inner products on the right or the left of the vectors. In this case, we put it on the right or on the left because they are just a number. Okay. And again, we recall the use of bra and cat. I think we have always say or use this term previously. Suppose we have the inner products of two Dirac vectors, phi and psi, like this. Suppose we detach the left hand side, that means the left hand side is this one, as a quantity bra phi. Does this have any meaning at all? So previously here, for example, if we use the cat, we say that vector phi. The cat basically representing a vector. Okay. What about if the bra, like this? What does it mean? So the quantity bra phi is a function, okay, which maps the vector space. That means a function to show how the vector space of the cat is arranged. So basically, bra phi is a function which map the vector space into the set of complex numbers with the properties of a vector space. So the properties is also a vector space. Okay. So basically, you can say that the bra is the function which describe the vector space, while the cat is the vector. So if we have these two jointed together in an inner product, so this is what we call as dual space. That means two, as if two spaces existing in one number. So the symbol like this is called the bra. It's just like revision, okay? And this is called the cat vectors. And when you combine them in an inner product, it's called bracket. Okay, actually bracket lah. Okay, bracket. Often, usually, cat vector, that means the one here, is representing vector psi A. Okay, psi A, X, or phi A for in terms of momentum, vector A. Okay, basically the cat vector is a vector to represent a vector, while the bra vector like this is usually conjugate of whatever, maybe psi B conjugate in terms of X or phi. That means the bra must be a conjugate usually. That's why when we have this, actually this equation is probability density equation. I think from the beginning we have touched on probability density. At those time we use this definition for probability density, basically an integral of between negative infinity to infinity. Then we have the term psi conjugate multiplied by psi dx. It can be represented by the inner products of the two psi. Okay, like this. So you can see here that the bra one is always conjugated. Okay, that's what is meant by this. Okay, the bra vector is usually conjugated vectors. Okay, some properties of the inner products. Okay, if we interchange the position of the bra and the cat vectors like this at any, I mean, as many dimension as we have, it is equal to 1. Okay, so basically it's quite similar with the probability density for a particle. For example, probability density for a particle, that means we normalize it, it is equal to 1, should be equal to 1. Okay, so you can see here that even if we interchange the position, it is equal to 1. Then if we have P, but P here is the whatever constant or function we have, and multiply with C cat psi here, then it is just the C here can be brought out, so CP vector psi, okay, or cat psi. If we have P for a summation of two vectors or two cat vectors, so basically it's just as if we multiply all the cat vectors individually and we add them up. If we have a vertical line like this with a P in between the two bra and cat, so basically we can just what you call it, just put the P together with the cat vectors. Okay, this should be angular bracket here. Okay, The dual of the vector p psi is simply, you see here p multiplied by the ket psi. If we change the position, the ket vector become bra vectors and p become adjoint vector or adjoint operator. Okay, so so you can see that p changes to adjoint p, while psi here is being changed from a ket vector to a bra vector. And remember that when psi in bra vector, it should be conjugated. Okay, so there is a change, not only just the symbol from the ket vector to bra vectors, but the psi itself inside the bra vectors is actually psi conjugate. Okay, so when we have this Dirac notation, time independent Schrodinger equation is simply h multiplied by ket vector psi equal to E energy ket vector psi, where h here is Hamiltonian. Okay, Hamiltonian means that it has the momentum operator and also the potential. As a conclusion, the inner product can be represented by the bra and ket vectors. Thank you very much for your attention.